This is the first video in the Exp and Log section. This is really just an introduction. Let's have a look at these graphs here. Here we go. So this green one the blue one going up here, 10 to the power of x. Okay, so as we increase x along here, we evaluate 10 to the power of x, and that's going to give us this line here. 0.5 to the power of x, well, this is less than 1, isn't it? So if we increase the exponent here to 1, 2, 3, 4, then actually we're going to reduce the value of this. Okay, so that's kind of going the other way. So this one is a growth, exponential growth. This is an exponential decay. And this green one is e to the power of x, where e is Euler's number. It's an irrational number. I'm going to come back to that in a minute, but its value is about 2.8. So you notice all these graphs evaluate to 1 when x is equal to 0. That's because anything to the power of 0 is 1. Okay. And this is called, these are called exponential graphs because the variable is the exponent. That means the power. So x is the exponent here, and so we get exponential graphs. Now, hand in hand with our exponential graphs, we have the concept of logarithmic graphs as well. Now, a log basically is the power of a number. So if we express a number as something to the power of something, then it is the power. So for instance, log of 100 is 2. Now that's if we're using base 10. Okay, so in other words, 10 to the power of 2 equals 100. So when we think of the log of 100, then it's that power, which is 2. Okay, so the upshot to this basically is that the exp and log are kind of opposite processes, and therefore if we take the, say, 10 to the power of 2, which is 100, and then take log base 10 of that, we end up with 2. So this is an important thing that keeps cropping up. Log base 10 of 10 to the power of 2 equals 2. So we'll come back to that idea. So let's just talk about Euler's number, because this is fundamental when we're talking really about most problems and aspects of Exp and Log. It's an important constant that is found in many contexts, the base for natural logarithms. An irrational number represented by the letter E. Euler's number is 2.71828, where the digits go on forever. That's an irrational number. And there we go. So that's been evaluated to about 100 places of decimal places. How do we calculate it? Well, E is actually the sum of this series, where this is 1 times 2, 1 times 2 times 3, or in other words, you would say that's 2 factorial, 3 factorial on the denominator, and if you've covered the binomial expansion and the binomial series, then you will have covered that. Here we go. Now this is an infinite series because these terms get smaller and smaller and smaller. So as we take more and more terms, we're getting closer and closer to the value of E. Okay, so all right, so this kind of gives rise to this function. We've just seen this on the previous page. So here we go. E to the power of x, and if you can remember all the projections of COVID, the spread of the COVID disease. They all kind of have this alarming thing, you know, in the early days, certainly, all this alarming idea that, you know, millions of people are going to have it by the end of next week. So that's what that looks like. So we should note that because E is a positive constant, then e to the power of anything is greater than 0. So if that x, that anything, is a negative number, then we're still going to end up with a positive number. It's just going to be smaller than 0. And of course, as we've said, e to the power of 0 equals 1. Now, sometimes we write e to the power of x, we sort of express it like this, exp of x. And this is sort of like, you know, sort of related to the function notation that we use. So it kind of, it looks a little bit similar to that, where the x is the argument of a function. So if we can imagine our process, we've got an exponentiating function, and we poke a value in there. And when we talk about it in general terms, that value is x, but we can sort of say x 2, which would be e to the power of 2. So that is Euler's number. Okay. And so the inverse function, which I prefer to call a reverse function, I think it's kind of slightly more meaningful, but is the natural log. So we talked before on a previous page about log base 10. Well, most of what we do in A-level maths concerns log base E. Okay, so that's why that's the main pair of functions that we tend to deal with, the exp of x and natural log of x. So that we call it the natural log. It's log base E. We could equally write it as log with a sub E of x, but it's universally written like this, and we often pronounce it as ln x. Okay, that n isn't a subscript, that's a normal size letter. Okay. All right, so what we got? So I mentioned e to the power of 2 here, evaluates to this number here approximately. And if we take the natural log of this number here, then we end up with 2. Okay. So I've said that log of a number is the power when expressed as base times power. If we graph these two functions here, e to the power of x, x of x, and the natural log of x, well, it looks like that. Now, if we stuck our mirror up this line here, y equals x, we can see these are sort of mirror images of each other. And that is what we're going to get because they are inverse functions of each other. Okay, so yeah, so just so we've noticed that e to the power of x is always positive, because e is a positive number. Then the natural log of x is well, we can only take natural log of x for positive numbers. That doesn't matter because we've only produced positive numbers from out e to the power of x. That's one way of looking at it, isn't it? Okay, so here we go. So it's gone. It's worth saying something about log base 10. We do still use log base 10. There are quite a few problems which involve log base 10 in A-level. But log base 10s were used very widely in the days before calculators. And they were a useful way of multiplying and dividing numbers if you had sort of several significant figures. And the reason for that is because logs are powers. If we want to multiply two numbers, When we express them as base times power, that means we add the powers. So in other words, 10 squared plus 10 cubed, just as a simple example, is going to be equal to 10 to the power of 2 plus 3. That's 10 to the power of 5. So, so by adding the logs here, we could get the log of a result. So the process that we went through is we would look up the logs of a number, base 10, and of the other number. We'd add those together, simple operation, and then we'd look back into our log table or our slide rule, and then we'll look up the number that corresponded to that log. So we use tables a lot, and also we use these things here, slide rules, which is another way of doing it, but we'll not go into that now. All right, so but log base 10s are actually useful because, you know, base 10 decimal, easy to work things out. Right, so we have I mentioned adding the powers when we're multiplying. Similarly, if we're dividing two numbers, we want to kind of work out what the, you know, what A divided by B is, then we could look up in our tables the log of A, its power, if we express it as 10 to some power, and the same for B. We'd subtract those, and then we go back to our tables and do a kind of a reverse lookup. All right, so so that's an important rule there. And also, if we have a look at this, you know, if we multiply n lots of 10 squared together, we're going to get 2 to the power 10 times 10 to the power of 2n. And similarly with log of 100 to the power of n, we're getting n lots of log to the power of 100, so that's equal to n log 100. So we can see here log 100 to the power of n equals n log 100. Okay, we could say log a to the power of n equals n log a. All right, so that's kind of, those give rise to our sort of our log rules. Certainly these first three log rules. So the log of x times y is going to be equal to the log of the log of x plus the log of y. The division rule as well, the power rule here. Now we also have another one here, which I've just kind of I'm throwing in, but we use this quite a lot. If we want to actually convert this to use a common base, then we use this little formula. So log base a of b equals log base c of b divided by log base c of a. Often this c will be Euler's number. So this could be quite important. We use this in you know, this comes up in certain problems, but actually if we ever want to evaluate the log base a and b where e is something unusual, maybe even a decimal, to, you know, 5.1 or something like that, we can do it on the calculator, so we don't really need to worry too much. But it does actually come up in some identity problems. We have to prove one thing, you know, is equivalent to another. Now, another outcome from all this is this particular identity. So if we're taking the log of a to the base a, then that's is 1. Okay. So, and that one is going to come up all the time. So again, that's just a consequence of all these other ones. Right. Okay. Yeah, so I mentioned the fact that e to the power of x, exp of x, and natural log of x are inverse functions of each other, and therefore e to the power of the natural log of x equals x, and natural log of e to the power of x are both x. So we're putting x into one function, we get something out the other side, then we put it through the reverse function, we end up with what we started. So e to the power of the natural log of 3 is going to be equal to 3, and the natural log of e to the power of 5 will be 5. That's what we're saying. So this kind of comes up quite a bit when we're solving equations and manipulating identities, because if our unknown is in the argument of a function, we want to get it down into the into the subject here. So if we're trying to solve for this, for instance, for x, then if we take the natural log of each side like this, then we're going to get the natural log of e to the power of x equals the natural log of 3. So take the natural log of both sides. And then this, by our identity above, is going to be equal to x. So this is typically what we do if we want to get the unknown out of the argument. This is what goes in the brackets is the argument of the function. We want to get it out of the argument into the subject line, like this. And then a similar example here, if natural log of x is equal to 3, then we could exponentiate both sides. Yeah, so e to the power of this equals e to the power of this, and this is equal to x, so x equals e cubed. Okay, so that is that. Right, let's have a look at an example. Given that y equals 3x squared, show that log base 3 of y equals 1 plus 2 log base 3 of x. Okay. All right. So first thing we're going to do is we're going to take the log base 3 of each side. Got a hint there, really, haven't we? That's, got y there. We need to do that. Right, okay, so what have we done here is these are two numbers multiplied. So the log of that product is the sum of the logs. So log base 3 of 3 plus log base 3 of x squared. And this, by the identity we spoke of before, is going to be 1. So that's fairly straightforward. Log base 3 of y equals 1 plus 2 log base 3 of x. And then hence or otherwise solve the equation. There we go. Right, okay, so right, well, we've established this. Okay, so in other words, log base 3 of 3x squared. Yeah, because this are equivalent, equals log base 3 of 28x minus 9. Okay, so we've just substituted log base 3 of 3x squared in for this. Therefore we can, we can exponentiate base 3 both sides. In other words, just strip out the log 3, gives us 3x squared equals 28x minus 9. And rearrange that to give us this quadratic, which we factorize to this, giving us this solution here. So, so that is sort of typical of the sort of problems that you might get in this category. And we're basically just falling back on those identities that we spoke of before. Right, I think we'll call it a day there. There are some worked examples on this which will help you perhaps understand a bit more fully. But well, that's it. Thank you.